Day number 7 on 4.2 will let us conclude 4.2, and there's two designs we're going to talk about. The first objective is to distinguish between a completely randomized design and a randomized block design, which is the new one. The second is know when a matched pair experimental design is appropriate and how to implement such a design. So let's go ahead and look at those. Before we talk about this second method of experimental design, let's just think about the caffeine example we did. Before, that was a completely randomized design where it was a comparative randomized design because we compared two different groups, the caffeine versus the non-caffeine. That was the simplest method, so it was great for us to use. But sometimes that method will not be the best because it will not yield the most precise results. There may be other lurking variables out there that we need to try to control, and there may be a different method to set up your experiment. Now, before we talk experiments, let's go back to the sample talk that we did before in section 4.1. There were 3 samples: the simple random sample, the cluster sample, and the stratified sample. Let's get rid of these 2 letters there. Within the stratified sample, that's where we created groups that were similar within each other, but they were different in between. And here might be a good example. What if I asked you in class here, I did a survey on how long it took you to do your hair in the morning. Would I just do a simple random sample of all of you guys, or would it be smart to maybe put you into 2 different stratum? One strata might be if you have long hair, and the other stratum might be if you have short hair. Because I would expect the long hair people are going to have similar results, and the short hair people would too. So in that case, it would make sense to put you into strata and then take my survey. Well, the experiment works the same way, but they don't call it strata. They actually call it blocks. So let's stick with that hair one. If I wanted to do an experiment with you guys about some new shampoo and I want to know how well it cleaned, I could probably assume that the people with short hair, it might clean your hair better if you use the same amount of shampoo kind of thing, versus the long-haired people. It may not clean it as well. I'm not sure, but that could be a lurking variable out there that could become confounding and have an impact on their response. So because of that, I would want to block for it. And I would just put you into 2 different groups, short-haired people and long-haired people. So this, what a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatments. So if I block you into 2 blocks, block 1 would be the long-haired people, block 2 could be my short-haired people. Now, to do an experiment on you guys, what I do is I just do a randomized block design. So once you've been blocked off, then I just do the same thing here. I would put you into 2 different groups, give you the 2 different treatments, and compare the results. And really what you're doing is you're looking at your first block and you just analyze their results. And then you look at block 2 and just analyze their results. You don't really ever compare how the 2 blocks look with each other in terms of your final experiment. Definition then is the random assignment of experimental units to treatments is carried out separately within each block. So if you think you need to do an experiment that's blocking, here's what you want to do. First step is form blocks based on the most important unavoidable source of variability. Find that most important lurking variable. If it's possible for you to put people or subjects into 2 unique groups where those groups are similar, do it. In doing that, you are going to block lurking variables and get some control in that experiment. Then we're going to continue doing what we did before. Just do randomization of putting the people into different groups for getting their treatments. And that's how you do it. So when it comes down to an experiment, the first thing you want to do is control what you can. Okay, I can make sure you all use the same amount of shampoo. I can make sure your hair is wet to the same level. I can control that. The next thing is block what you can't control. I can't control your hair length, so I'm going to block you by putting into 2 groups, and that takes care of that lurking variable. And then I am going to randomize to take care of even more lurking variables and also to create some comparability amongst the groups. Okay, let's look at our first example. Does a new detergent clean better in warm or cold water? And they're going to wash clothing by hand, by the way, not in the washing machine for this. So let's just talk about some of the key things before. Experimental units, explanatory, response, and treatments. Now for this experiment, let's talk about what the experimental units would be. The experimental units are the various articles of clothing that are going to be washed by hands. The response variable is almost easier to talk through next. Here's the experiment. Does a new detergent clean better in warm or cold? So the response variable is going to end up being the cleanliness of the clothing. Okay. The explanatory variable you want to think about, is it dealing with the detergent or the temperature of the water? In this case, it's going to be deals with the temperature of the water being used. So then our treatments are going to end up being connected to that explanatory variable, the temperature of the water. The treatments are going to be very two different levels of that explanatory unit. The cold water and the hot water are the two levels of our factor that we're using, thus giving us two different treatments. Now, as you set up this experiment, you want to think about things you can control and things you can't control. First thing here, things you can control. Before you even start designing this, you want to say, okay, if we're going to wash clothing, let's make sure the same person is doing the washing, especially if it's going to be washed by hand. That is definitely a controllable lurking variable. A non-controllable lurking variable. Now, another lurking variable you might think about is how the clothing gets washed together. If I were to take a pair of blue jeans and a t-shirt and I'm washing them by hand in the sink, if you ever watch the water, it turns blue. What's going to happen is that t-shirt is going to get some of that color, which is going to cause my response to be impacted. The cleanliness of that t-shirt is definitely going to be not as clean as I would like it to be. So this is a lurking variable that we can actually control. We can block for it, and that's exactly what we would do. We would take the shirts and the clothing and put them in two different blocks based on their color type. Then we're basically going to go back and do what we did for our caffeine experiment. It's almost like you're doing two separate experiments. So once I put them into light colors versus dark colors, and then I'm going to switch over and do my randomization of putting them into either the hot water or the cold water. By randomly assigning the clothing to either the hot water experiment or the hot or cold water, that's going to take care of any other lurking variables I couldn't control. Conduct the experiment, come back, and actually compare the cleanliness of just those light colored clothings to each other and make a conclusion with that. Then you would do the same thing with the dark color clothing and make a comparison with that. Now, the one caution the AP board will say is this: do not confuse blocks with treatment groups. Okay, our treatments in this case are very specific. The hot water and the cold water are the two treatments. Remember, the treatments are going to be related to that explanatory variable. The blocking, if you look at the question up here, does a new detergent clean better in warm or cold water? Never does this question in our research talk about anything about the color of the clothing. So the treatment group is really addressed in the question of our research. Hot or cold water is our explanatory variable that we're using. The block is a lurking variable that we have to think about. It's never going to be directly stated to us. So just know the difference between the blocking part versus the treatment. Now here's another example when blocking would come into play, and let's just get the terminology down. Annie is an avid baker who would like to compare two different chocolate chip cookie recipes, A and B. So she recruits 10 volunteer taste testers to rate each cookie on a scale of 1, which is very bad, to 5, which is very good. She will make 10 of each type of cookie, and we have our 2 cookie types, for a total of 20 cookies. Each cookie tray will hold only 10 cookies, so she will use 2 trays, and bake them at the same time in the same oven. 1 sheet on the lower rack and 1 on the upper rack. If you've ever cooked cookies or cooked anything in the oven, it's going to cook slightly different. So the cooking on the lower rack versus the upper rack could make a difference. All right, because cookies might bake differently depending on which rack they're on, we will use the 10 locations on the lower rack sheet as one block and the 10 locations on the upper rack sheet as the other block. So what they're doing is they're going to control the lurking variable of how well things cook on the top of the oven versus the bottom of the oven. We can control that, so we block it. And this is the block right here. Okay, on each of the sheets, Annie will randomly place 5 of each type of cookie. So she's coming in here and doing the random assignment now and putting 5 somewhere on one cookie sheet and 5 on the other places on that same cookie sheet. And then she's going to do that same thing for the bottom rack. And then once the cookies are done, she will actually have her subjects taste the cookies and then compare type A versus type B. So what we've done in this thing is we have controlled really for the variability in the cooking in the oven, which part of the oven is the cookie being cooked in. So we've controlled that with the blocking, and we've controlled that with the randomizing where they go on the actual cookie sheet itself. You know, and let's think about these 4 elements of experimental design. Now in this, the experimental units are actually the location in the oven of each of the cookies. Because if you think about it, we have the 2 different trays at different levels, and there's 10 different spots on the cookie sheets. So the locations is what she's experimenting with. Then the explanatory variable in this case is going to be the cookie recipes. The response to that explanatory variable is the rating scale in terms of taste that the cookies are going to get. And the different treatments in this case, remember treatments are related to the explanatory variable, which we also call the factors. So if the explanatory variable or the factor is the cookie recipe, there's going to be 2 levels of cookie recipe treatments. It's going to be recipe A and recipe B. And that's what we see here is the treatments are shown up in this part where we have you're either going to get type A cookie or type B cookie. Okay, let's look at one more. A better texting example. A cell phone company is considering 2 different keyboards, either design A or B, in its new line of cell phones. Researchers would like to conduct an experiment using subjects who are frequent texters and subjects who are not frequent texters. The subjects will be asked to text several different messages in 5 minutes. The response variable will be the number of correctly typed words. Part A, explain why a randomized block design might be preferable to a completely randomized design for this experiment. Let's just take a moment, if you want to pause this video, identify the experimental units, explanatory variable, response variable, and treatments for a moment. So I'm going to pause the video and have those up on the screen for you after you've done that. Okay, so our experimental units, they're subjects. We're using people. The explanatory variable in here is the keyboard design. The keyboard design is going to give us a response of the number of correctly typed words. And the treatments that we're using are either the keyboard A or the keyboard type B. Now, why is it that a randomized block design is preferable in here? It comes down to this right here, that we have frequent texters and we have non-frequent texters. This is a lurking variable that could impact if you think about the response. If you're not a good texter, you're not going to type a lot of the words correctly. If you're a good texter, you're going to be a lot better at this. So we want to control for that lurking variable. Therefore, what we would do is we would block on if you're a frequent texter versus a novice texter. If you want this in written out form, here is a potential answer you could say for this. Because the subjects include people of varying text abilities, a completely randomized design would lead to a lot of variability in the response variable. However, in a randomized block design, the experienced texters would be compared to each other, and the novice texters would be compared to each other. This would make it easier to see a difference in the response variable if there is one. Okay. Let's look at part B for this one now. And actually do what it says is they want us to design the randomized block experiment using 100 frequent texters and 200 novice texters. So I want you to think about what the block design would look for this. In total, we're going to start with 300 subjects. Then we're going to take those subjects and block them out. Then we're going to do random assignment. We're going to apply the 2 treatments and compare. So if you want to take a moment and sketch what you think this block design would look like kind of as a tree diagram, go ahead and do that. I'm going to pause the video for a second and go on to the next slide, which shows you what the block design looks like. This right here is how you would do the block design. Again, we have 100 frequent texters, 200 novice. We start with 300 subjects. We break them up just like it says. This right here is our block. We've now controlled a lurking variable of your texting ability. The next thing we're going to do is randomize. This is going to help us take care of the additional lurking variables. We're going to randomize you to either test the first keyboard, type A, or the second keyboard of type B. After they do that, let's compare these results just for the experienced texters and see what we conclude about our experiment. Do the same thing for the novice texters and can make a conclusion about your experiment. Now be careful if this was on the AP exam and it said to outline the randomized experiment. The diagram here would not be sufficient enough. You would include a diagram and the language on how you would do that. So don't forget to say something like this. To randomly assign the experienced subjects to the two groups, put 50 slips of paper labeled A in a hat and 50 slips of paper labeled B in a hat. Mix up the paper and have each subject select one to determine which design he or she will use. That's for our experienced folks. Follow a similar process for the 200 novice texters. After the experiment, compare the mean number of words correct for the two different block designs within each. So you would want to talk about what you would analyze in terms of the response variable. Keep in mind, we're not technically ever comparing what the two different blocks look like together unless we wanted to make some conclusions, but that's not the intention of a block design. It's just looking at the final thing that we're trying to measure, which is what we think of the keyboard design. And we can look at the keyboard design based on looking at our experienced texters and see if it makes a difference from the novice. If not, we can then make some conclusions. Which keyboard design we like better, is A or B going to be working more appropriately? Now, if you want a little bit more practice on this, this is on page, I believe, 251 within your book. I would encourage you to read this data exploration and just answer, what do you think they're going to block on in this particular example? So if you want to take a moment, pause the video and read this. When you go, the next slide that pops up will actually show you the answer. So go ahead and pause if you want some more practice. In this particular experiment, because we're using different brands of tires, it would first be best to block by each brand of tire. So put each type of tire in its own group to study, and then apply a randomization, and the treatment would be this. If we just look at Michelin tires, we would do a group that has one air-filled tire and then one nitrogen-filled tire would be one block. Maybe the next type of tire would be a generic tire. You would test that one in another block and so forth. Now the second type of experimental design is a matched pairs design, and here's what it is. It's a randomized block experiment in which each block consists of a matching pair of similar experimental units. It basically comes down to this. It's a special case of randomized block design using blocks of two things. So let me give you an example. What if I was a medical company and I currently have this pain reliever and I wanted to make some improvements to it to see if it was better? So I'd have my original pain reliever in this new formula. So to test it out, to see the impact of my old versus my new pain reliever, I could create a block of two people. I might have subject 1 and subject 2. And what I would do is figure out through randomization who gets the first pain reliever. Maybe it's this guy. And then this person gets the second pain reliever. I would do my tests on these two, and then I would compare these two results by finding the difference in the old and the new pain relievers. And that could tell me if the new pain reliever was actually making the difference that I wanted it to. And that's the key here. When you assign, for example, those pain relievers, chance must be used to do that. That's what makes this two-person block design, that it's associated by chance on who gets to do what treatment. So that's one of the cases. The second way you can do matched pairs design is actually have a block of just, in your pair, it consists of just a single unit or subject, and they get two different treatments. In this case, when we're doing pain relievers, would it make sense to have like in the same day have subject 1 come in and take pain reliever 1, later on in the day take pain reliever 2, and compare the results. That doesn't logically really make sense. We could maybe spread that out over various days, but if they want to do it at the same time, you could actually just break it up all at the same time, have subject 1 take something and subject 2 take a different medicine and compare. What if I want just the same subject to do something? We could. In this case, you can do a matched pairs. You have one subject, and you're going to have that subject do 2 different things and compare the results. In just a second, we're going to look at what if you take your pulse rate when you're sitting versus standing. So if they want to know if it makes a difference, we're going to take your pulse rates. At the end of the study, we're going to compare your 2 results. Now, this is very similar kind of to what we did in the caffeine experiment, where you guys were each your own subject. You had your starting pulse rate and your ending pulse rate, but your starting pulse rate and ending pulse rate weren't the 2 treatments. Those were just how we measured the response. So don't mix these 2 things up. What we would have had to have done in the caffeine experiment, if we wanted to make it a matched pair, I'd have to give each of you the same of the 2 treatments. So I'd randomly pick when you get the cola with caffeine, and then I'd say when do you not get the cola with the caffeine, which again would not make sense for setting up this experiment. So just don't confuse the fact that on the caffeine example, we did your pulse before and then your pulse after taking the treatment. In that case, the pulse before was actually establishing the baseline prior to doing the treatments, whereas in a matched pair design, one person actually gets 2 of the treatments, which again in our case would not have made sense. Okay, here's one I talked about just a little bit ago, the standing and sitting pulse rates. What they would do for this is you could do completely randomized design. You would, just like we did for the caffeine experiment, half the class would sit and take your pulse, the other half would stand and take your pulse rates. If we did that, the results could look something like this. This is a dot plot of the standing pulse rates. Here's a dot plot of those with the sitting pulse rates. Then we could go in and take the means for that. The mean for those standing was about 74.83. The mean for those sitting is this. And we can compare the difference and see that it looks like the pulse rates went up by 6.5 beats per minute, I'm assuming here, which is higher. Clearly, based on the math there, it seems like the standing is higher, but there's a problem in that the variability of this creates a lot of overlap, so it's not convincing. When you look at the dot plot, there really is a lot of overlap in here, right? There's not much difference. We can tell there is some difference, but we really want to see it in a stronger, kind of more clear way. So what they're going to do is say, let's just do a matched pairs design. So instead of putting you guys in really just one big group and giving you each 2 different treatments, we're going to block you in this matched pairs design. So I'm going to do a matched pairs design and have subject 1, right? I'm randomly going to figure out if you stand or if you sit first. Maybe this time you're going to sit first, then you're going to stand, take your pulse rates, and then we're going to measure the difference on those 2. So get the difference for each subject. We're going to plot that difference right here. Subject 2 would do the same thing, plot the difference. When you do that, you can actually see this statement clearly. The variability in the response is reduced. I mean, the variability here is only going roughly from about, between the 0 and 20, but versus up here, we definitely have a lot more spread. So it's less variable, and you can definitely see a more clear-cut answer in terms of this. The mean standing pulse rate was higher. In this case, it was 6.8 beats higher when we did a matched pair on this. And if you look at the count on that, 21 out of 24 had a higher standing pulse rate. So it's just a lot easier to show the results doing the matched pairs in this and making a good conclusion. Now that last matched pairs was using one person as a block and doing 2 treatments to that person. This is an example of having 2 different people in the block and giving them each an individual treatment to do. And what they've done in this case is we are doing a cholesterol drug. They're testing out the current cholesterol drug that they have, and then they're testing out a new drug they have. What they've done in this first one is just a standard comparative randomized design, again, like the COLA example we did. They put these people in two different groups and then randomized who got which treatment and recorded the results. Again, we see tons of overlap. We see a lot of spread. So it's kind of hard to really get a good analysis going on this. What they've done instead is they blocked it off and did, again, subject 1, subject 2. That's one particular block. You could say it's their matched pair. And then they're going to randomly figure out who gets which treatment. This might be the new treatment. This might be the current treatment. And then they're going to look at the differences between that. And then they're going to plot the difference on the dot plot. Here you can see the difference in the drug. For every single matched pair, every scenario showed that this new drug by far did make a difference. And you just get a much stronger statistical data to back up your research with this. So we've gone through plenty of examples here on the randomized block design and a few on the matched pairs. Hopefully that helps. When I get back to class the next day, any questions you have on this we can definitely talk about.